Okay, I make it 5 past, so I'm going to start with the webinar. So a couple of things before we start. Firstly, the session's being recorded, so just so you're aware, what we'll do is we'll do some post-processing of it and then put it up on the ARCHER2 website and on the ARCHER2 YouTube channel for people who couldn't manage to be here. If you have any questions as we're going along, please do feel free to interrupt me. You can ask either via the chat or via just turning your speaker on. If you're really polite, you can use the put your hand up feature. I'll try and keep an eye on that and hopefully spot when people do those things. If I don't, there's hopefully some people from EPCC on the call as well who can give me a prod to tell me that that's happened. And finally, an apology, my dog's in the room behind me, and she has a chew at the moment. So if you hear any chomping noises, that's not me eating at the same time as giving a webinar. That is my dog chomping behind me, but hopefully she won't be too noisy. So let's get started. So the point of this webinar was to try and give you a heads up on some of the differences between ARCHER and ARCHER2. Now, I know we've done this sort of thing before. In one of the previous webinars, we talked about the ARCHER2 hardware and software, which highlighted some of the differences. But now we've had access to EPCC anyway. I've had access to the 4-cabinet and TDS ARCHER2 systems, the 4-cabinet system probably for a week or so now, and the TDS for a little bit longer than that. It seemed right to be able to give you an update based on our experiences so far, so you knew what to expect from the new system when it comes online. And what I would say is we don't know everything yet. We haven't had a chance to explore all of the differences now. I'll highlight some gaps in our knowledge as we go along, but I will do my best to answer any questions that people have. And if I don't know, I'll just say I don't know, and we'll go away and try and find the answers and put them into the documentation or future material and things like that for people. So without further ado, let's get started. And I've got a standard slides with about sharing material, and also with all the ARCHER2 partners, which is UKRI, particularly EPSRC and NERC, EPCC, University of Edinburgh, and PrgEnv-cray, who are providing the hardware for the new service. Okay, so what you may or may not know, I don't know how closely you've been following the way the ARCHER2 is going to be deployed, but initially ARCHER2 is going to be deployed as a 4-cabinet system, and then in the new year, the rest of the hardware will be added, the other 19 cabinets, to take it up to a full 23 cabinet system. And at some point, once the 4-cabinet systems moved into service, then ARCHER itself will be shut down, and the ARCHER2 4-cabinet service will be the national service for a short while, hopefully until the rest of the hardware is available. So what I thought I'd start out by is giving you a heads up about what the differences between the 4-cabinet service, the one that's going to be coming soon, versus the full system, where compared to ARCHER itself, to give you an idea of what is and isn't available and what to expect in the short term, and then in the longer term when the rest of the hardware arrives. So the 4-cabinet system is exactly the same sort of system as the full system is going to be. It's just a smaller version. It's a HP-Cray EX supercomputer that was formerly known as Shasta, when Cray were a company in their own right before they were bought by HPE. It's in Edinburgh. It's got 1,024 compute nodes in its 4 racks, and that gives it just over 130,000 cores, okay, which is slightly larger in terms of core count than ARCHER is at the moment. But I should say it's got a lot less compute nodes than ARCHER, and I'll provide a few more details on that in the next slide, in a few slides' time. And each of the compute nodes has 256 gigabytes of memory. It's got one file system, which is almost 4 petabytes. It's got all of the home storage that's due to come with the ARCHER service itself, which is a petabyte. It's got the new Cray interconnect, which is it's called Slingshot, which I'll talk a bit more about as well, though we have less details on that. 2 login nodes, and the idea is that any data that you have on the 4-cabinet work file system will be made available on the full system when that switchover happens for a period of time to allow you to copy the data across, because we only have one of the work file systems here, the full cabinet system, not the full set of work file systems available. The full system itself is, again, same sort of architecture. It's got 23 cabinets rather than just the 4, so it'll have close to 6,000 compute nodes and almost 750,000 cores on the system. It's pure CPU. There's not anyway a significant GPU fraction, though there is potentially a small what HP called a collaboration system, which may have some AMD GPUs for people to be able to explore and play around with. We don't know much about that part of the system yet. It will eventually have 4 file systems, or with just about 14.5 petabytes of luster. It'll have a solid state burst buffer storage type system. It's going to have a solid state burst buffer. I say burst buffer. That's one of the use cases for the solid state storage. There are potentially others. It's a bit more flexible than that. Hopefully, we know more about that closer to the time when it arrives with the full system. It's going to have the home file system, which is all there on the 4 cab anyway. And again, the slingshot interconnect. Okay, sorry, let me skip back to the next slide. Okay, so here I'll try to give a table that just gives some sort of comparison of services. And this is a comparison of both like hardware resources and also software and some other bits and pieces that I thought were useful or interesting to note users. So we've already talked about the different sizes of the systems. I think one of the implications of the difference, particularly between Archer and the 4 cabinet, is that although the 4 cabinet system has potentially more cores, it has probably about a fifth of the nodes available. So the throughput of the 4 cabinet system, because a node is the minimum unit you can require, is going to lie somewhere between that of the total core count and the node count for Archer. So I think it's going to have less sort of throughput capacity than Archer, even though it's got slightly more cores. But it's not as bad as the sort of 5-to-1 ratio, which you naively assume, because I think because of the high core count on each compute node, that quite a lot of jobs will require less nodes on Archer on the 4 cabinet system on Archer 2 to give the same performance as you got on Archer. So if you think of the sort of equivalent in that way, then the throughput's somewhere in between the node count and the core count in comparisons. One thing the 4 cabinet won't have is high memory nodes. On Archer 2, I didn't mention these, but some of the compute nodes will have 512 gigabytes. They're the high memory component. That's not available. Could be available on the 4 cabinet system. It's just the 256 gig nodes. We've got less login nodes, which gives us a bit less redundancy if something goes wrong with a bit of hardware. The biggest problem in terms of redundancy for the 4 cabinet system, I think, is the fact that there's only one work file system, one parallel file system. So if we have issues with that, then that causes a problem for everybody. You know, on Archer, because we had 3 file systems, we could, if there was a problem with one of the file systems, at least temporarily shuffle people across to other file systems to ensure that they could keep running. I mean, obviously data access will be a problem if the file system was down, but some people that's easy and they can just pick up again, and some people it's harder. But we won't be able to do that on the 4 cabinet system. But we will be able to do it fine on the full system when it arrives, because it will have 4 file systems rather than just the one. Solid state file system, I've already mentioned, is coming with the full system. And the job schedule has changed on Archer 2. It's going to be Slurm. I'll give some example job submission scripts later to give you an idea of what that looks like in terms of compared to Archer, which was PBS, which was different, and other Slurm systems which you may have used elsewhere. Also on the 4 cabinet, we won't have the serial queue, the PP nodes, as they're known on Archer. They're coming with the full system. They're not available on the 4 cabinet system. We'll have 3 compiler suites, as we do on Archer now, except that instead of Intel compilers, we'll have the AMD compiler because we're using AMD processors on Archer 2. The idea is that we'll have singularity containers available. They're not quite available yet on the system as we have it at the moment, so they may not be quite there for the start of service on the 4 cabinet system, but we're hoping they'll come online soon after that. But we'll see how we go with progress of getting them up and running. And finally, in terms of the RDF, for those of you that use it, on the full system, there's going to be a mount on, at least on the login nodes of the RDF file systems, but on the full cabinet system, that's not going to be there. So if you want to transfer data from the RDF to the full cabinet system, it's going to be via SCP or something like that. What we're looking at doing at the moment is setting up the connection between the Archer login nodes and the ARCHER2 login nodes, and potentially RDF access nodes in the feed after that, so that you only need to use a key to access ARCHER2 from Archer. You don't need to input your password as well. That should mean that you can use Archer serial queues and things like that to transfer data on the RDF to ARCHER2. Yes, Dario, you have a question?
Sorry, let me unmute myself. Yeah, just quickly, ARCHER2 full cabinet. Can you say, and is it going to run alongside ARCHER2, or is it just a temporary machine?
Okay, so the full cabinet system is going to have a period of overlap with Archer. We're still a bit unsure of how long exactly that overlap will be. The challenge is that to be able to fit the full ARCHER2 system in, we need to remove Archer from the machine room. Okay, so the idea is that the full cabinet system starts, there's an overlap between Archer and the ARCHER2 full cabinet. And then at some point, Archer is switched off, the full cabinet system keeps running. We take the Archer system out of the machine room and put the rest of the ARCHER2 hardware in, and then there's a step in the future somewhere where the full cabinet system gets merged into the rest of the hardware. There'll be a short amount of downtime to make that happen, and then it comes back up as the full 23 cabinet system. So the idea is the only break in actual service is that bit where the full cabinet is merged into the other 19 cabinets to make the 23 cabinet system.
So this full cabinet are going to be part of the full system. It's not in addition to the full system. So
yeah, exactly.
The full system is going to be 5,800 nodes, not 6,800 nodes.
Yeah, exactly. The full cabinet is sort of an earlier delivery of the some of the hardware.
Thanks.
Okay. On the other side of things, the service provision, the bits from EPCC, which are the service provision part, which is the project user administration safe, and the service desk where you can ask queries, the system administration to maintain the system and connect it up to all the infrastructure, the network and the power and the cooling and all that sort of stuff. And the CSE service, which does the in-depth technical support, training, ECSE, all those sort of things, they're already fully staffed and fully operational. So there's no change in the level of service from them between the full cabinet and the full system. And they should all that stuff is accessible to users from the start and from day one, and should be there for you. So that's a bit better than the sort of more the halfway house with the hardware side of things. Okay, so that was a sort of high level overview. I wanted to go into a bit more detail about the comparison with Archer on both sort of the hardware side and the software side, to give you an idea of what to expect. So first of all, on the sort of technical hardware side for the compute nodes, and to give you an idea, what I tried to do here is give you an idea of what the differences and the change in balance is between an ARCHER2 compute node with the specifications listed down here, and the Archer compute node, the specifications listed down here, and how that ratio compares. So where it's green, ARCHER2 has the bigger number than Archer, and where it's red, Archer has the bigger number than ARCHER2. Essentially, that the green and red are maybe a bit provocative here. They sort of imply good and bad when that I don't think that's actually necessarily true. Maybe I should have used neutral colors here. But they're different. First of all, they're different processor manufacturer. Okay, so Archer, probably as you know, ARCHER2 probably as you know is going to be an AMD based system, whereas Archer is Intel Xeon. And the major difference I think between the two systems, the major difference between the two systems is the core count per node. On ARCHER2, there's going to be 128 cores per node. That's 2 times the 64 core processors, whereas on Archer it's obviously 24 rather than 2 times 12 core processors. There's a similar number of cores per NUMA region because there's more NUMA regions on an ARCHER2 node. They're more complicated architecturally. What this actually means is the floating point performance of a compute node on ARCHER2 is almost, it's like 380, almost 400 times more than on Archer. Okay, so there's a huge increase on the per node compute power anyway, and that's significant because the smallest amount of resource you can request on Archer 2 in the same way as Archer is a single node. Okay, so that's the smallest unit of resource you can request on the system. And actually, there's actually an increase in the floating point performance per core, even the cores have almost twice the floating point performance of an Archer core. In terms of memory, there's a lot more memory per node, but actually, because there's so many more cores per node, sorry, it looks like that should be 3.84. Sorry, yes, you're right. I've got the decimal point. Sorry, I've got something wrong there in terms of the count and the number. Sorry, Michelle. Sorry, yes, you're right. My ratio is wrong there. Okay, in terms of the memory per core, I'll correct that on the slides that go up on the website. Thank you for pointing that out. Should check your slides more carefully before you present them. Is the lesson there? So the memory per core is actually lower on Archer compared to Archer 2. Okay, with and there are more memory channels, but there are more memory channels per socket. So what we found actually is the memory performance per node is very good on the system, and some cores can benefit from that. The NUMA structure is very different as well. Sorry, some codes can benefit from that. The NUMA structure is very different as well. So investigating the best way of how to use memory and how you're using MPI processes and OpenMP threads is going to be key to getting the most out of Archer 2. The memory is a lot faster as well. So there's a change in the memory and the amount of memory bandwidth. Why are there two numbers? Because there's the standard memory nodes and the high memory nodes. So these the memory per node is the 256 for the standard memory nodes, and for the high memory nodes that will come on for the Archer 2 system, there's 512, and the same for Archer. There's standard memory nodes and high memory nodes. The same is true in terms of the memory per core. And in terms of the bandwidth, there's a lot more bandwidth available on per node, but again, because the core count is high, actually the amount of memory bandwidth available on a per core basis is lower on Archer 2 than it is on Archer. So what I was trying to get at, I think, and try to summarize in this slide is that the balance of Archer 2 compute nodes, the power in Archer 2 compute nodes is different from Archer, right? There's more cores per node, but less memory and memory bandwidth on a per core basis. There's a very different cache and NUMA structure. So thinking about how you best exploit the node and experimenting with it is going to be key to getting the most out of it, because it's not like you're just going to be able to go, I think, with the same number of cores as you would on Archer for some codes anyway, and just expect it to work in exactly the same way and give you the exact uptick in performance. You know, for some codes, particularly those which are sensitive to memory bandwidth or memory capacity, you're going to have to explore how you can use maybe less MPI processes per node, exploit threading, understand how that plays around the NUMA structure. I think there'll be probably quite a lot of people not using all the cores. And also, what I haven't mentioned here, of course, is the interconnect and how that fits into things here. You know, how much interconnect resource is there on a per core basis, because that particularly affects things like MPI collective operations and how much you can get on and off a node on internode communications going forward. So I think there's going to be a lot of time for experimentation. We've started doing some of that as the CSE team, and obviously we'll publish any data we have and any advice we have as soon as we have it available. But we have had, in terms of the full 2-cabinet system with all the sort of right bits in place, we've essentially had about 24 hours of access at the moment. So we really haven't had a chance to explore that in very much detail. We're working through our list of things we need to check and do. So we don't have that advice right at the moment. So that's a bit about the compute nodes and the compute node architecture differences. In terms of software, I've already mentioned the change in compilers, the main change being the change from Intel to AMD with no Intel environments available. Similarly, things like density linear algebra through BLAS and LAPACK and also Skill LAPACK are provided by Cray libsci, and often people on Archer will use Intel's MKL. That won't be available on the new system, but you can use libsci, and that's available on Archer as well. FFTW is provided by Cray, again a Cray library. MPI is Cray MPitch, as it is on Archer, so that should be familiar to most people. There's a bit of a change in terms of the debugging tools available. So rather than the ARM Forge stuff, the DDT and things like that, there's the command line tools, which is a special port of GDB, which HP Cray provide, which supports parallel debugging and memory debugging from Valgrind for HPC, which again is a special parallel port of the Valgrind tool that Cray provide. In terms of profiling, that's actually more similar to Archer because it's the Cray path tools generally. We do have map available on Archer as well, but and that won't be available on Archer 2. But I think most people who've been doing profiling on Archer tend to use Cray path anyway. And there's some new stuff coming that isn't available on Archer and Archer 2 as part of the Cray provided software anyway. There's going to be HP Cray now provide a Python environment. And if any of you use the tier 2 system down in Bristol, provided by Bristol by GW4 Isambard, and you'll have seen that there's a Cray Python environment on there. So that's not just the new to Shasta systems, it's just newer than Archer. And that provides things like MPI for Pi, NumPy, SciPy, and Dask, I think the parallel task parallelism tool, which you can build on top of with your own environments on Archer. There's also an R environment provided by Cray. We haven't had a chance to play around with that very much, so I can tell you less about that at the moment. And finally, there's a set of deep learning tools, which I think are optimized tools to support things like TensorFlow and PyTorch and things like that through the Cray Python environment as well, though we haven't had time to really play with those yet either. So I want to say a little bit more about the compilers because there is a change for the Cray compiler environment for people who've used that, the PrgEnv-cray. The change there is that the C++ compiler on the Cray environment is moving from the Cray proprietary stuff to a Clang based implementation, which should mean for people who want to use C++, that it's much easier to use that Cray programming environment. It uses standard flags and it compiles much more quickly than the old Cray C++ compiler, and it should be more standards compliant as well and keep up to date with newer standards faster than the original Cray version. The Fortran compiler in the Cray programming environment is still based on the proprietary Cray Fortran compiler. That's just at the moment, there's no real equivalent in LLVM for Fortran at the moment. And Cray still think they have things to offer the Fortran compiler, so they're keeping that available. GNU hasn't changed at all, still GCC, G++, G-Fortran. The AMD environment has a C++ compiler, Clang, again, and the Fortran compiler is based on this PGI version of this. So I had a chat on the RSE Slack yesterday, which was illuminating about the different versions of Flang that are out there and how they all are called Flang, but aren't all the same thing. So the AMD one is based on this PGI version of Flang, not the F18 Flang, which can't actually compile code at the moment, which is part of and that's the bit that's part of the LLVM project. Okay. So they're the three program environments at the moment. Our initial experience is that they all just work fine generally. We've seen good performance with both GNU and Cray. We've had less chance to explore the performance of the AMD compilers. But that's on the list of things to look at as well. It's just quite a long list. Okay, so that's my sort of comparison of the systems. I wanted to really give a sort of a more overview rather than focused on the difference on Archer 2 and this is what's going to be provided within Archer 2 itself. So this is my sort of diagram of an ARCHER2 compute node with two sockets. These are the two sockets here, socket 0, socket 1. All of them are, and each of these sockets is made up of one of these AMD 7742 processors. And each of those processors has 4 NUMA regions with 16 cores each. And it has this infinity fabric, and that's used to connect both the compute cores out to the bits of memory, also to connect the two sockets to each other within the node, and finally to connect out to the interconnect as well. And you can see that there are 2 interconnect interfaces per node, 1 per socket, where the network interface chip, the NIC, goes out to the slingshot network. I'll say a little bit more about the slingshot network in a minute, not in very much detail. We may get a presentation from Cray on that, webinar from Cray on that in the future. But essentially, it's an Ethernet-based network rather than InfiniBand or Aries or the other things you might have come across before. On Archer, there was 1 NIC shared between 4 nodes, and it was connected to 1 socket, and then you had to go via the internal node interconnect to get to the other socket. So there was an extra hop there, and that's not the case for ARCHER2. Now, most applications didn't see that actual function, though you could if you looked very closely at the MPI performance numbers, but you shouldn't see that at all on ARCHER2. Each of these 16-core NUMA regions is made up of 2 8-core complexes, which have the 8 compute cores, some L2 cache, and some shared L3 cache between the 8 cores. And then they go out to the Infinity Fabric to talk to the other cores on the processor, on the socket, and then off to the other socket as well. And so that's the sort of architecture, the base architecture of the node. And I think we're still, we haven't had very long on the system to explore the performance. We're still understanding what the impact of this sort of different architecture, particularly the reference to the interconnect, where there's 2 interfaces out to the interconnect. Both of these are 100 gigabit per socket per second interfaces, so that's 200 gigabits per second per node. Okay, so we're still trying to understand how that works. Yes, was it Patrick had a question? Nope. Okay. Casper has a question.
Yes. Do you know if the slingshot NICs have affinity to any of these NUMA regions, or is it just the level above in the NUMA hierarchy?
No, so I'm not quite sure what you're asking.
Because in principle, you know, the slingshot, if you look from the point of the NUMA regions, the slingshot should be closest to the NUMA 0, NUMA 1, NUMA 2, NUMA 3, or it can have the same NUMA distances to all 4 of them.
Okay, fine. So yes, it should have the same distance to all of them because the Infinity Fabric is sort of a central. There's no concept. So I've drawn it here just for convenience.
Again, because you know, on the normal one, you usually PCI Express slots have are closer to 1 of sockets.
Yeah, but I don't think that's true. I think it's the same distance from the slingshot to all of these different NUMA regions.
Okay, thanks.
Okay. In terms of the programming environment modules, the initial system is based on environment modules v4, which are similar to ones that are, in some senses, the ones that are on Archer at the moment. Cray are bringing support for LMOD, hopefully later this year, and we're going to switch to that as soon as it's available because there's various advantages in terms of the functionality available to users to express dependencies and to do intelligent things around modules that otherwise wouldn't be available. So we want to take up that option as soon as we can. The major difference from Archer is how you access the different program environments. So instead of module swap PrgEnv-cray to PrgEnv-glue, you now do something just module restore, PrgEnv, whatever you want. The program environments are now module collections rather than actual real modules themselves. This is the same is going to be true in LMOD as well. Excuse me. If you need to load the program environment to the batch script, then you need to pass actually a full path to these modules because the way collections work is they're stored in a hidden directory in your home directory, and the home directories aren't available on the compute nodes on Archer 2. So if you wanted to compile on the compute nodes, you would need to do something clever. The way we're going to do it is we're going to set up an environment variable for all users by default that allows you to get at these without having to actually type the full path. And that means that if things change in the future, we should be able to seamlessly pass it through to users with no problems. So that's a bit of a change from Archer 2. Sorry, from Archer to Archer 2. Cray are providing, as we talked about the numerical libraries. They also provide HDF5 and NetCDF. We talked about the MPI, and their toolkit also supports OpenSHMEM, CoRA, Fortran, and Unified Parallel C. I've talked about Python and R already, and I've talked about the debugging and profiling stuff. So we've already covered these things, so I won't spend any more time talking about them again. The idea for CSE, the CSE service from EPCC, we have an initial list of software that was agreed with the research councils that we should provide, and that's what we're working to in the first instance. Now, I should say that this doesn't mean that other software won't be installed. So this isn't set in stone, and it will change over time as people's requirements change. But just to note, this is the initial set we're working to. And I don't expect everybody to read through that and things like that. People could ask, are you going to support software X then? The answer is always, in some sense, because even if you just want to compile it in your own directories, the CSE service will provide support through the service desk to help you do that. If you run into problems, you can always ask us for help to install whatever software you want to install wherever. This isn't the list of software. This isn't a list of software we'll help you with. It's a list of software we're planning to install centrally, at least in the first instance that we're working to. So I wouldn't regard this as prescriptive in any way. I think I've talked about Slingshot, Ethernet based, 2 times 100 gigabits Mellanox network interface cards per node, and then there are these go to the switches, which are 200 gig per port. So actually, there is the potential to support faster interconnects on the node than we have at the moment, faster NICs on the node than we have at the moment, or higher bandwidth NICs than we have at the moment. At the moment, there are 2 underlying software interfaces. The default on Archer 2 that we've had a chance to have a go at is the Open Fabrics interface, OFI. They also support UCX. We haven't had a chance to explore the performance differences, if any, between these 2 different options at the moment, but we'll do that and provide more information on that going forward. But just to be aware, if you get on the system, you can try out these 2 different options and see which one works best for your piece of software or what you want to do. Another thing is that unlike Archer, where static linking was the default, Archer 2 only supports dynamic linking executables at the moment. Static linking isn't supported at all. But it may come in the future. I think there's an aspiration from PrgEnv-cray to provide this feature in the future. Now, the compiler wrapper scripts do automatically add the paths to libraries from the PrgEnv-cray Pro environment into the binary run path, which means that they can be found at runtime without needing to load the correct modules, say in your job submission script or stuff like that. But because it's run path and not R path, if you load a module with a different version from the compile time, this supersedes the version that's built into the binary. So you can take advantage of newer modules, newer software without having to recompile, unlike if you use R path rather than run path. We're looking at the moment at how we can make the CSE provided libraries and software all behave in the same way, so that when you build them with the compiler wrapper scripts, that the right paths get embedded into the run path, so that you don't have to load the modules in your scripts. We're still testing this. As you can see, there's still quite a lot of things we're still testing here because we haven't had access to the system for very long yet. Yeah, I don't think there's anything else to say there at the moment. As I mentioned earlier, the scheduler is Slurm. So this is an example, basic MPI job submission script on Archer 2. The bits that are missing are the partition and the quality of service specifications, and they're different for different queues, essentially. Whether you're running in a long queue, standard queue, short queues, things like that. Those things will change. But essentially, you specify the number of nodes you want, the number of tasks per node you want, and the CPUs per task. So this is for a this is just like 4 nodes, fully populated, 128 cores per node, and place 1 MPI process on each of the on 1 MPI rank on each of those cores. We always recommend exporting OMP num threads equals 1 unless you're using threading to stop any of the sort of system libraries or performance libraries exploiting more threads and potentially overscheduling on cores. And then you don't specify in your run line how many MPI things, how many MPI tests and things like that you want. They're just taken directly from the SBatch options with SRun. Things get a bit more complicated if you want to do hybrid type of job with MPI and OpenMP. This time we've got 4 nodes. We want to run 8 tasks per node. So that's 1 MPI rank per NUMA region, and then 16 threads per MPI rank, which is matches onto the NUMA layout of ARCHER2 compute nodes. So this is essentially saying 4 nodes, task per node 8, and this sets a stride of 16 cores between each of those MPI processes to make MPI for the OpenMP threads. And then we set OpenMP threads 16, give it a hint about how to place them, and there's some other options about how you distribute the tasks around the node. There is a session on Slurm next week, with a webinar on Slurm next week. It's going to be one of our colleagues. They'll go into more details about how Slurm on ARCHER2 will work and how you specify more complex layouts. What I wanted to give you an idea here is just about how it would work in general, and with a couple of examples for you to see. So it's pretty standard Slurm. There's nothing magic or new there, or especially different for ARCHER2 compared to other systems you've used that use Slurm. Okay, I'm getting towards the end of my slides. I think now I had a few quick slides on performance that we've had a chance to measure so far, and then I've just got a sort of conclusion slide, and then hopefully time for some questions and stuff like that. What I would say about my performance data is my caveats are that it's performed on the system really with a sort of pre-release version of the system software. So it probably, be careful of that. I haven't done any optimization investigations. I managed to compile the codes and check that the performance was sensible, and then look at how it performed. I haven't explored compiler flags, different programming environments, different potential numerical libraries, or anything like that. And I haven't really had a chance to do many, or sometimes any, repeat runs to capture variability in performance, though the system has been quite quiet because it's only been the CSE people, it's only been the EPCC people on it so far. So hopefully that means the variability should be limited, even if there was any. So, and I've got just 3 different codes I've managed to look at so far, and only for a limited number of data points. So the first one I've got here is GROMACS. The art to say about this graph is that up is better performance. The orange curve is ARCHER2, the 4-cabinet system, and the blue curve is ARCHER itself. And this is a small 1400 K atom test on GROMACS. And you can see we don't go up to very many cores here because this is a small system. We're not looking at scaling out to very high core counts here at all. ARCHER2 generally looks pretty good for GROMACS so far. I mean, the limit of scaling's reached here at about 2024 cores, which is 16 nodes on ARCHER2. The ARCHER results keep scaling a little bit further because the lower core counts per node and the less saturation in the interconnect. But generally, the GROMACS performance is pretty good. ARCHER2. If you look at a single node performance comparison, this is a per core comparison. But if you look at pure single node comparison, which is the smallest unit you can take, an ARCHER2 node gives you about 5 times, or just over 5 times, the performance of an ARCHER node for this GROMACS benchmark, which is quite good and seems to scale pretty well out to the scaling limit anyway. you get over 49 seconds per day on this benchmark using ARCHER2. Looking at moving on to look at Caster. This is again a quite small benchmark, or I think on the Caster website it's described as a medium-sized benchmark, where it really doesn't scale out very far. You can see the core count's very low here. Even on Archer, you get out to probably what's this, 1, 2, 4, 8 nodes, probably, if that, in terms of scaling. On ARCHER2, you can only really scale this one to 2 compute nodes before the performance turns over, and this is suddenly just beyond the scaling limit. You start to get hit by all-to-all performance with too many small messages, particularly in this benchmark where we're fully populating all of the cores on the node with MPI processors. So there's there's 128 cores per node, 128 MPI processors per node. You start to saturate the network, I think, on this small calculation. We just scale up too much. But again, the sort of per core performance comparison is pretty good. And if we look at a single node again, you get about almost 7 times the performance out of an ARCHER2 compute node. Of course, it has more cores than an Archer compute node for this Caster benchmark. My final example is an Open SPLI CFD example. This is one of the benchmarks that was used to procure ARCHER2. This one scales out much further. You can see here I'm out to just over 30,000 cores on the ARCHER2 curve, which is the grey curve here. And again, per core performance looks very similar to Archer, a little bit better than Archer on a per core basis, which is sort of what you'd expect. And the scaling looks fine out to about 30,000 cores. And if you look again at a node comparison, this time we can't compare a single node. It's too large for both Archer and ARCHER2. It takes up too much memory, so it can't be one of a single node. So the smallest common node count I could get it to work on both of them was on 5 nodes, and you get about 5 times the performance on 5 nodes on ARCHER2 compared to Archer. Of course, again, there's a lot more cores there, so that's not really a hugely fair comparison, though, because that's the smallest unit that can be requested by people. Actually, that is what people can request on the system. So, in terms of the application's performance, actually, it's looking pretty decent from the limited tests we've done so far. Oops. So that's me towards the end of my talk. So in summary, the full cabinet service, which is the bit that's coming first, will have a similar core count to Archer, but with fewer nodes. It's got a bit less resiliency and reduced functionality compared to Archer. And I've talked about some differences in the module environment and the batch system, though the batch system is pretty standard Slurm, so it's probably familiar to a lot of people who use other HPC systems. The full set of EPC supports available for the full cabinet service, and initial performance results look promising. There are still some issues on the system, I think, and so we still don't have full understanding of how the system works and how best to use it, given the small amount of time we've been on it. But actually, so far, we've made a lot of progress in a short amount of time, I think, in terms of exploring the system since we've had access to it. So I'm happy to take any questions or points, and I'll do my best to answer them if possible. But thank you for your attention, and thank you for taking the time to listen. Dario.
Just a couple of quick questions. The first is, what is the proportion of high memory nodes? And the second one is Slurm supports task farming, which, okay, you didn't have the time to show it in your example, but will this be supported on the system? Okay.
So in terms of the proportion of high memory nodes, I would have to go away and actually look up the number. I'm sorry, I don't have it off the top of my head. I have a feeling, no, I'm not going to say anything because I'll just say the wrong number and give you the wrong impression. So once I finish answering questions, I can go and have a quick look and see if I can get the answer quickly for you. In terms of task farming with Slurm, I'm not quite. Is this at the level of using job arrays, or is this within individual task farming within individual jobs that you mean here?
No, individual jobs.
Okay.
You do test run, then code, and then you put the the background symbol at the end.
Yeah.
And you put this into a loop.
Yeah. No. Okay. So yes, no, that does work. We've tested that. So you can have multiple S runs within a batch script, and actually you can subdivide the nodes in that way. So the smallest amount you could request is one node, but then once you've got your one node, or however many nodes you want, you could use them in any way you want. So you could have, say you got one node, you could have 128 S runs, ramp runs at the end, and a wait at the end.
Right.
And it should. I think there's some. You need to do some work to get them on the right cores. I can't remember exactly the syntax, but you can do that.
Okay, thanks.
There you go. Thank you, James. So there you go. 292 high memory to compared to 5,556 standard memory nodes. So it's quite a small proportion. So I'm happy to take questions from anybody else. So Dimitri. So would serial nodes for small intensity, single low number core jobs, pre-processing, and massive data downloads be available? So the answer is yes on the full system, but no on the but not on the full cabinet system. Okay, so that bit, the hardware, the bits of hardware that support that, the pre and post processing stuff, and the serial jobs, are not coming with the full, are not available with the full cabinet system. They're being shipped with the rest of the system, so won't be available until the full system's available. Which I realize means, you know, I do know that makes it difficult for some people's workflows on the full cabinet system, but that is the way the system is being delivered by PrgEnv-cray, so we don't have any control over that. And Doug's asking, would the serial nodes be the same architecture as the compute nodes? Yes, so that's one of the big wins over it compared to Archer, is that it's exactly the same processor everywhere. The login nodes, the serial nodes, and the compute nodes are all exactly the same processor, which makes things much easier compared to the serial nodes on Archer, where they were old Westmere's or something like that, and they had a different architecture. Hans asking, when will Archer 2 be in service? So, okay, so the timelines are still a bit unsure because we're still ironing out problems. What I would say is we're aiming for early user access. There's a subset of users who are getting early user access. We're aiming that to start sometime early next week. Okay, with full user access for the full cabinet system to start sometime after that. It depends how quickly we can get the final bits and pieces ironed out, how quickly we can get people on. I would think within a month we'd hope that within a month we'd hope to have users on to the full cabinet system, unless something really disastrous goes wrong between then and now, given what we've seen. So that's the full cabinet system. For the full system, the plan at the moment is it to be shipped this year before Christmas, and installed into the machine room before Christmas sometime this year, with the sort of commissioning work to happen straight after Christmas. And then user access to start as soon as possible after that. George is asking, sorry I missed it, what was the interconnect topology? Will be the same as the pilot system? Yeah, so the interconnect's the same on the full cabinet system and on the larger system, just a larger version. It's PrgEnv-cray's new slingshot interconnect. The topology is Dragonfly, which is the same, with the same sort of diameter as Archer at the moment, which is maximum 3 hops between any 2 nodes. The major difference of it, I think, actually compared to Archer, is the fact that it's Ethernet based. Rather than anything else. It's RDMA over Ethernet, RO. RDMA over converged Ethernet, ROCE. Doug's asking, how long after the full cabinet system is live will Archer be switched off? That is yet to be decided. I think it depends how well, does depend a bit on how well the full cabinet system is able to support the user community and but there is a decision point. There are decision points in the future about when to switch our Archer off. Patrick's asking, mention new parallel debuggers on Archer, one of them being how do they work with the batch system? Okay, so there are a couple of different ways that debuggers can work with the batch system, and you know about how you can set breakpoints and things like that within a batch system. The two main ways are that you can use an interactive job, so you can srun directly from the command line on the login node to launch your program. So essentially you start the parallel debugger and then you can use that to launch the program directly from the login node. So you have your parallel command line debugger terminal there, and you can then make breakpoints in the usual way you would, and they get passed through to the parallel processors that are running on the back end compute nodes. Okay. The other way is to start up a job and then start a debugging session again on the login node in the command line, and then attach that debugging session to the running job. So you can get the information from the job that allows you to attach the debugger to it, and then start and then debug in the same way you usually would with GDB. Jon is asking, will jobs require small numbers of cores, share a single node, or is each node exclusively used by one job? The minimum unit you can request for a job is one node. So you will always have exclusive access to a node. You can't share it with anybody else. If you've got small, if you have somebody that wants to use less than 128 cores per node, you still have to request 121 full node, and you'll be charged as if you're using one full node in your budget. But as we mentioned to Dario earlier, you can task farm within a job onto that node, onto separate cores in the node. So you could run 128 single core processes within a node, or 2 64 core processes, or whatever you wanted. And once you've requested a node, it's just that nobody else can come onto your node. Okay, but it's up to you how you want to use that. Casper, will you allow SSH access to nodes allocated to a user? The answer to that one is don't know yet. It has been mentioned. We don't know if the architecture supports it yet, so that's to be confirmed. Okay, I'm not seeing any more questions right at the moment. We are at 3 o'clock there, so I guess I'll stop now. I mean, there are plenty of other sessions coming up and webinars and chances to ask questions. So please keep an eye out for them, and I posted a link to one of them above for the Slurm session next week and maybe some of the others. Thank you for coming along. I hope you found it useful and interesting. If you want to review the slides and the recording, they'll be up on the website as soon as we're done processing them and made them available to users. Thank you very much.